So this presentation is OSPF to the customer and peering with your customers using OSPF. Why, how, what about security? So my name is Tomas. I'm from Slovakia. I work for a company named Atris. The company has been around since 1991. We do networking, servers, virtualization, IP security system, ISP networks, etc. I'm responsible for network design, security, wireless, a lot of work with servers and virtualization. I'm a MikroTik certified trainer and consultant. So for this presentation, our goal is to show peering options for providers to peer with their customers using OSPF, and to test this setup in a network simulator using a virtual simulated network, so using actual MikroTiks and GNS3 on Windows. For the agenda, we'll go over OSPF basics and concepts. We'll go over OSPF area and LSA types, some example topologies and some example solutions. Route filters and security, and then the topology simulation in GNS. So for OSPF, OSPF is a dynamic routing protocol. It stands for Open Shortest Path First. It's an interior routing protocol based on link state and is used for inter-AS prefix distribution. OSPF v2 for IPv4, OSPF v3 for IPv6. So why is the OSPF in this solution? Of course, because it's a dynamic routing protocol, and therefore it provides us with dynamically assigning gateways and redundancy and other very good advantages. And it will give redundancy to the customer. It can provide easy load balancing to the customer as well. So why OSPF and why not BGP? OSPF is faster. Yes, I know that's not really a great argument to make, but it is faster. It is also easier to configure, and for your important customers, which are enterprises and other big institutions, their network engineers will have much less trouble configuring OSPF rather than BGP, and also a lot more network engineers today actually knows OSPF rather than BGP. And OSPF is supported on all business class devices, even the cheap routers these days. You can have a router from Viger, from Zyxel, from whatever. They actually support OSPF these days, whereas BGP is still very little supported on cheap devices. So why OSPF and not BGP is mostly for the benefit of your customer. So OSPF basics. OSPF gathers link state information from available routers and constructs a topology map of the network. So it supports full CIDR as opposed to RIP. It calculates a path through the network, and the path through the network is formed based on shortest path. So the shortest distance from node to node, from hop to hop. And each interface in OSPF configuration has a distance parameter. So basically OSPF routes IP, so layer 2 traffic, but it also uses IP as its own transfer protocol. And on layer 4, it has its own protocol, so OSPF protocol number 89. So if you're doing some firewalling, etc., you need to actually allow a layer 4 protocol 89 to pass through firewall from your OSPF peers. Multicast is used for packet delivery in a single layer 2 domain. There are different interface types which use broadcast or a point-to-point communication, etc. But by default, multicast is used. So if you are somehow blocking multicast on your switches at layer 2, OSPF is not going to work. I've seen this quite a few times actually, that ISPs block multicast and then OSPF doesn't work. So OSPF is a link state protocol, like we mentioned. So each router interface, from the perspective of OSPF, is a link. And OSPF sends LSAs to its neighbors on these interfaces, on these links. And LSAs are basically link state advertisements, and it's a very simple update on a router's link state. So one will be sent when a link is connected, disconnected, changed, etc. So how a path is calculated through the network? Each OSPF router gives a topological database. So a topological database is just a table in memory that contains link information about all known routers. Then an SFP, so shortest path first algorithm, is used to calculate the shortest path to all destinations in the network. And an SFP3 is formed, listing all the routers and listing all the routes to any destinations with an order of preference. So how the OSPF process actually works, first of all the routers exchange LSAs, so they talk to each other. Then they form a topology database, which is kept in memory. Then the algorithm is run on the topology database, and the shortest tree, so the SFP3 is calculated. And then the resulting calculations, the resulting shortest paths for all destinations are injected into the routing table. This is a simplified version, but that's basically what's being done. OSPF can have multiple areas. So OSPF actually divides its networks, or can divide the network into areas. So an OSPF domain can but doesn't have to be divided into areas. And each OSPF domain, so an OSPF domain needs to have a backbone area. If you are running multiple separate OSPF instances over your network, etc., each one needs to have a backbone area, but usually we just want to have one OSPF domain divided into the multiple areas or one big flat area. And each additional area needs to be connected to the backbone area. OSPF doesn't really impose any limits on the number of areas or anything else. The only limit is that they need to be connected to the backbone area. So each area has a unique ID. For example, backbone is 000, and there are multiple area types. Basically, there are 5 main types, or 3 main types, and 2 subtypes. In this presentation, we will go over the standard area type, the totally stubby, and or not so totally stubby area. So we are talking about LSAs, and that is the main topological informational unit transmitted in between routers. So each area type accepts and forwards different types of LSAs. There is 7 types of LSAs. The ones that are important to us actually are type 1, 2, 3, 5, and 7. So type 1 is just a simple notification about the router. You know, I am a router, I'm on the network, I'm here. Just notifying other peers that I'm a router. Type 2 is used within the local layer 2 network. So the routers talk to each other and exchange the information about their local network. Then the type 3 is the summary LSAs, where all the networks, all the other networks that the router has connected to it are exchanged through type 3 LSAs. Then we have type 5 LSAs, which are external LSAs, which are routes or destinations injected into the OSPF process externally. So these might be your static routes that you inject into OSPF, or BGP routes that are being injected into OSPF, etc. And then there is type 7 LSAs, which are important for us. And they are basically just type 5 LSAs in disguise. So type 7s are just type 5s used in an NSSA area. And I know this is a lot of lingo and everything else, but hopefully it will make sense in a bit. So what do we actually need to configure for OSPF to run and to run it properly? For OSPF basic config, we need a router ID for OSPF. OSPF process can actually select a router ID from the IP address table of the router by itself. There is a process how a unique router ID is selected, etc. But of course, for our purposes, it's best to specify our own specific router ID that each router will use. And this router ID should be a reachable IP address on a loopback interface, and this is important. So it will actually need to be injected into the routing table of all the OSPF domain, and also on a loopback interface. So when any of the interfaces go down on the router, it doesn't cause a flap on that interface. So it will be always reachable since a loopback interface is always running. So a really easy and fast config would be just to create a bridge for loopback, then add an IP address, /32 IP address on the loopback bridge, and then we will actually use that /32 IP address as the router ID for this router. So what this does is actually it just creates an IP address as /32 that's always reachable on a bridge that's always up and uses that as a router ID. Of course, the router ID has to be unique for each router in the OSPF domain. So we would just implement these IP addresses by one. Since it's a /32, you can just implement it by one and use a separate /32 on every single OSPF router in your network. So making the loopback reachable, for the easy configuration, there's two options. Either we enable redistributing connected routes inside of OSPF, inside of the instance. That's the easiest way, and we could just do all we need to do. The drawback with this is it will actually redistribute all the connected IP addresses or all the connected networks on that OSPF router. So if you have multiple, it just depends on what you want to do and if you want to redistribute everything or not. But if you just want to include the IP address for the loopback, so the router ID IP address inside of the OSPF process without actually including all the other connected networks, you just go into routing OSPF network and add the /32 IP address from your loopback into the backbone area. So either of these two options will achieve what we needed to do. It's just a different way. So the default route for our network. So on our edge routers, in our provider network, preferably we would want to distribute our default route also dynamically from OSPF. We can either get this default routes then from BGP or whatever else, usually that's BGP. Just internally, since we may want to run BGP internally as well, but if we don't, this will just redistribute the default route to our edge routers, to all the other routers in the OSPF domain. So we just said for this instance of OSPF, we distribute the default route from the edge routers as type 1, so we would only run this on the edge routers. And that means just like this dynamically without adding any static routes on any router, if we just configure all of this on a router that has interfaces with IP addresses and subnets, OSPF would take care of all the dynamic routing, all the networks as usual. We would have a default route on all the routers, etc. So we were talking about areas. So OSPF domain can be divided into areas, as we said. And areas are implemented in OSPF for performance, for network topology separation, and for security reasons. A lot of networks these days actually run a single flat area OSPF network. There's a good reason for that. These days, basically in the old days, OSPF takes quite a bit of memory, and the SPF calculation can take quite a bit of CPU if their topological tables are really big. But these days routers have really fast CPUs and a lot of memory. So a lot of networks that don't need the actual separation from areas will actually run a single flat area network, which is not bad at all, but for our topology, we actually want to use multiple networks to get the separation, or multiple areas to get the network separation from the areas. So let's look at the area types that we were mentioning before. So normally when you create a area in OSPF, the area would be of the default type, and the backbone area, where normally all the OSPF routers, all the OSPF peers communicate, is also of the default type. So in the default type area, the routers exchange the type 1 and 2 LSAs. We mentioned that just type 1 is the router itself informing its peers that it's a router, and the type 2 is just the connected subnet information. But in the default area type, the routers actually exchange type 3 and type 5 LSAs in between each other. So the whole network, every single router in the network is actually notified of the topology of the whole network. And for the default area, for all of our provider routers, that's just completely fine. It's used inside of our network. All our topology knows its IP addresses, all the prefixes, and how to reach them, and that's good. But this is not secure at all to peer with our customers. So customers could see all our internal routes, all our internal subnets, all the IP addresses which are used, which are not used, etc. And our customers could even inject routes into our routing tables, which is not a good idea at all. So the default area is completely fine for the purposes that of our routers communicate with each other, but for peering with our customers, we need something else. So with peering with our customers, since we mentioned there are multiple area types, the totally steady area is the best choice. It provides exactly what we need. For a totally steady area, type 1 and 2s are exchanged, which is completely fine because the router knows that it has another provider router on the other side and it knows the connected subnet. So those LSAs can be changed without a problem. It's not a security threat. And the only other thing that's actually pushed through the OSPF process is the default route to our customer. So the default route would be dynamically pushed from OSPF. We could change the IP addresses of this router, we could change the IP address of the scheme, the router could die, etc. It doesn't matter since the default route is pushed dynamically through OSPF. So we can use this area type to peer with our customers because it only gives them the default route and nothing else. They cannot push anything back to us. It's exactly what we need. So for an example, topology and a basic example, if a provider wants to provide redundancy for the customer, just peer with OSPF with the customer, create a separate area for your customers, set it as a totally stubby area, and peer with the customer. So the customer router, there is a /28 subnet here. The provider has two routers with two separate links to the customer. One of them might be wireless, the other might be fiber. So fiber as the main route, wireless as the backup, or wireless as the main route, and DSL as a backup. It doesn't matter really what layer 2 is, as long as it's Ethernet and can transfer the IP on layer 3. So just like this, we would provide a completely redundant link to our customers, and this should remove 95% of outages for the customer. Of course, we are talking about outages which are caused by the provider network problems, not by the customer himself. Because in this case, since the customer only has one router here, that could still go out and he would have an outage since he is not redundant there. But for basic redundancy from the provider side of networks, and also this is not for your basic home and little users, provider, home users and non-important customers. But if you have big customers that are important to you, that take a lot of bandwidth from you, this is a really simple way how to offer them redundancy. And of course, with RouterOS, OSPF and all of this is supported on any router board. So how to configure all of this? We simply create a new area to peer with the customers in this OSPF area. So we would just add an area, give it an ID. We would say inject summary LSAs, no. And this actually defines that this is a totally stubby area instead of just a stubby area. We give it a name and the type stub. So it's a stubby area, but inject summary LSAs says it's a totally stubby area. Then we would add the OSPF network. So this is the network we are connected to the customer. Add it to the customer's area. And then we would create a OSPF interface, give it a name, and use authentication with a password. So OSPF security part 1, always secure your OSPF interfaces with authentication. And this, of course, prevents unauthorized routers to establish an OSPF connection. Of course, it's just an MD5 authentication that can be broken, but it's, of course, much better than nothing. You can then establish IPsec or anything else to encrypt these OSPF sessions, of course, just use IPsec in transport mode. But for basic protection, it's better than nothing. If you want it to be really protected, IPsec transport mode. So all we have done is we have created the area for the customer, set up an OSPF network to peer with the customer, and use authentication for the OSPF peering of the customer interface. So that was a basic example. If the customer decides that he actually needs redundancy on his part as well, it's really easy. Customer can just add a second router to his edge, and this would provide full redundancy to the customer. So you would, for example, have a fiber optic line down here and a wireless line down here for backup. It can be both fibers, etc. It doesn't really matter, as I said before, the layer 2 is. You would just create two separate subnets. In this case, it would be /30s, for example, and then you would peer inside of these /30s. So on our provider customer 1 and provider customer 2 routers, how would the config look like? It's very similar. We would simply create an OSPF area, let it be a totally stubby area, so type stub and inject summary LSAs no. insert on each router the proper OSPF network into the customer area, and then use authentication for the OSPF interface. So that would basically give the customer complete redundancy from his side of routers, from the provider side of routers. Of course, then the customer can either use VRRP or another, hot standby protocol on the local network, or if he's running a bigger routed network down here, he will also probably use OSPF inside of his own network. But so what if the customer wants even more? We are giving the default route to the customer redundantly already, but customers at this level of their networking and at this level of their requirements usually need public IPs. And these public IPs should also be redundant. And usually the customers will request those public IPs to be usable anywhere in their networks. So those have to be routed public IPs which are routed to them, which is really common. So how do we achieve all of this with redundancy and with everything else with OSPF? The area type we can use for this is totally not so stubby area. It's a wonderful name, I know, totally not so stubby. So what totally not so stubby does, it's basically the same as the stub area, or as a totally stubby area, that only type 1 and 2s are exchanged between the routers and a default route is pushed to the customer. But one difference with the totally not so stubby area is that the customer can push type 7 LSAs to us. If you remember, we mentioned that type 7 LSAs are just type 5 LSAs in disguise for the usage of totally NSSA areas. So our router would actually translate those type 5s, those type 7s into type 5s and then push them into our OSPF cloud, into our OSPF domain. So the customer can actually inject their own routes into our routing tables now. So we just assign them a prefix, a certain IP range, and they can dynamically push the IP range by querying with OSPF with us. So what's necessary to configure all of this? So on our provider to customer 1 and provider to customer 2 routers, we would simply create an OSPF area, give it a unique area ID, again set inject summary LSAs no, give it a name, type NSSA, so it's a totally NSSA area like we mentioned, and translator role for our provider routers, we always want to translate those type 7s into type 5s. Then create an OSPF network to peer with the customer on each router, the proper network, and again, just add the OSPF interface with authentication. So what we actually configured here is that customers will get a default route from us, but customers will also be able to inject routes into our OSPF domain. So what about security then? Because customers could theoretically inject routes into our routing tables to route traffic to them, the traffic that is not supposed to be going to them. So they could inject prefixes which are not their own and then mess with our network. So this is of course dangerous and needs to be secured somehow. And how do we secure this is with routing filters. It's fairly easy actually. You just tell the routing engine to only accept certain prefixes from certain peers. So in this actual example, in our actual topology, we would allow our customer to push the local prefix that we are peering with him on, because that will still be exchanging LSA, so that needs to be enabled. So for our outbound to him, we would only give him the default route and nothing else. And from the inbound LSA, so for the inbound peering from our customer to us, again, we have to allow the local prefix because we are peering on that prefix with our customer. And then we would give him a range of IP addresses that he is able to announce to us. So for example, in this particular case, this is just a imaginative public IP address range, but we would configure that our customers can inject into our OSPF domain these IP addresses from this prefix, and for the prefix length of 29 to 32. So he could actually push any /32 out of that prefix to us, or any whatever. So you can separately configure what prefix lengths he can push inside of the prefix. And then we would just discard all of the OSPF advertisements from this customer. So the result here is that customers will be able to inject routes for only their IP ranges into our routing tables. Redundancy will still work completely, and the OSPF peering with the customer is secured. So what about load balancing? And since we already have 2 routers and 2 links implemented, why not implement load balancing at the same time? And it's possible with OSPF. So customers can actually load balance their outgoing traffic already to us as they like over the 2 connections. Because for us, we will be receiving the traffic and just routing it away. For us, it's not a problem. The traffic can come on any link. So outbound load balancing is really up to the customer, how they define it. They can use PCC, they can route 50 to 50, they can use only failover. It's completely up to the customer. Our routers will just take the traffic and pass it along. But customers can load balance their incoming connections as well by manipulating the OSPF path costs within their OSPF sessions to us. So the customers themselves can actually manipulate how the incoming traffic is load balanced as well. We don't even have to do anything. They can use ECMP if they want. So if the costs for both links are the same, ECMP will automatically route packets, 50% over one link, 50% on the other link. And this is really advantageous because we achieved full load balancing for the incoming and for the outgoing connection, and the customer can configure the load balancing how they like and change it without causing reconfiguration on our end. So the customer can actually have full load balancing or have only failover. It doesn't matter to us. We don't have to change any configuration on our end. We don't even have to mess with anything. Everything is down to the customer. How he manipulates his OSPF interface cost is up to him. So all the customer needs to do is manipulate their OSPF interface cost, and everything will work, and it will behave, load balance, or failover, depending on the configuration, without our interference. So let's look at a more complex topology. In this example, an ISP would provide connectivity over PPPoE to the customer. So OSPF peering would then be established inside of the PPPoE session, and this all works with the same config as above. There is no changes to the OSPF config, really. So this would be a fully redundant network on the part of the customer and on the part of the provider. You can see that each customer edge, so CE router, has a separate connection to our provider to customer routers. We then have an MPLS or a VPLS backbone in our network. We have some VPLS tunnel terminators, which are also redundant. And then we have 2 PPPoE access concentrators, which are also redundant. So CE router 1 and CE router 2, which would each establish a PPPoE connection to their own provider PPPoE access concentrator. So, as I've said, let's look at all of this in GNS3 with MikroTik. And this is GNS3 running on Windows on a little laptop that has just about no CPU power. And we are simulating here this whole MPLS, VPLS network with OSPF peering, with everything, but as I've said, on Windows even. So all of these examples that I had in this presentation here can actually be easily simulated in GNS. And you can try how they work. If you want the GNS topology files, just let me know, I'll mail them to you. So for example, let's look at our tunnel terminators. So this would be one of our tunnel terminators here. Let's see here. So you can see that we simply have a single bridge configured for our PPPoE tunneling. So the bridge has a VPLS interface and an Ethernet interface in it. So just a tunnel terminator for VPLS passing it through to the PPPoE concentrators. Let's look at the PPPoE concentrators here. Actually, let's check if the VPLS is running. Alright, so our VPLS tunnel is running. over the simulated connections inside of GNS3. Everything seems good. Basically, if we want to take a look at the performance of this laptop, it's just a dual-core CPU at 1.8 gigahertz on this laptop. You can see that it's running everything really smoothly. The only problem is if I want to power on this topology, it actually takes 10 minutes. Once the topology is powered, everything is running nicely. You can even push traffic to this topology. I pushed 5 megabits through this topology and it doesn't match the CPU. So 5 megabits through this simulated topology was about 80% CPU. You can see the CPU spiking when there are some keyboard lives, etc. But as I said, power on about 10 minutes, but after it's powered on, everything works on a little laptop. On Linux, this would be no problem at all. Basically, the hypervisor that GNS3 uses, which is QEMU, doesn't support native virtualization on Windows, so it's only running pure software virtualization on Windows. On Linux, QEMU actually supports KVM, so on Linux, this whole thing would be actually hardware virtualization accelerated, so it would run without a problem. But as I said, the point was to show that you can actually run all of this on Windows. So let's look at our simulated access points, or access concentrators for PPPoE. All right, we seem to have an active session from our customer. That's good. He's getting an IP address and everything. So let's look at which means that our provider to customer routers are also working correctly. VPLS sessions are up. They are breached to the customer, so the customer is just getting layer 2 PPPoE here and nothing else. It's breached through the VPLS, MPLS backbone all the way to the tunnel concentrators, and then it's breached again to the PPPoE access concentrators. So let's look at the customer routers, see if everything works there. And so now that's the provider to customer router. Here we go, customer edge 1. So you can already see some things to Google. Alright, it seems to be working just fine. So this whole actual topology is even connected to the internet through the MOM wireless on my laptop. You can simply, this is a host interface in the cloud, so it's bypassed to my laptop's wireless network connections, which is then passed to the provider edge routers. They're actually masquerading this whole network since we don't have BGP sessions in them up. So yeah, you can actually set all of this up, connected to the internet, test it completely all in a simulation for $0, €0. This is using demo licenses from MikroTik, so 24-hour limitation on the licenses, but you can actually get them for free as well. So just power it on, 0 investment, and you can create a whole provider network just like this with redundancy and everything else. Alright, so that's really it from me for today. If you like this presentation, you can find more material from me and more of my presentation on TikTok. I have some IPsec presentations. I have an MPLS for ISPs presentation from just this year in the US, where you can see how to make the whole PPPoE over VPLS setup. It's an hour-long presentation which gets heavily into MPLS, into MTU problems in MPLS networks, etc. So just go to TikTok, you can search for any of these presentations. If you have any questions, go ahead, you can ask me right now, or you can find me after the presentation. So which part of all of this mess did you not understand? And thank you for listening.